Welcome to the lecture on the MGLRU algorithm. So this is a variant of LRU and MG stands for multiple generations. So the idea here is that any kind of a page management algorithm has a proactive component and has a reactive component. A reactive component is that you want to bring in a page, there is no space. Well, at that point of time, you have to do something, which means evict a page in from main memory to the swap space. The proactive component basically means that on a periodic basis, you scan the list of pages that are there in main memory and ones that are not frequently used are pushed out. So MGLRU has both. It relies mostly on proactive, less on reactive. So its key idea is like this, that you take a group of pages and assign them to a generation. Later on, we'll see there is something called a sub-generation also, but let's live with the notion of a generation. Higher the generation, the more recently accessed it is. The largest generation is the most recently accessed, right? The earliest sequence number or the earliest, the smallest sequence number or the earliest generation is the least recently accessed. So the nice thing about this is that this is like the thing, right? This is exactly what Linux implements. So it can take the priority of a page into account, whether it is dirty, clean, modified, not modified, all of these things can be taken into account. So what it basically does is that it maintains a range where maximum sequence is the latest generation, minimum sequence is the earliest generation. And if assume that the generation of a certain page is G. So the generation, the sequence numbers always get incremented, they never get decremented. So if this is getting incremented, in a certain sense, pages in generation G are getting aged. Why? Because with respect to the maximum sequence number, their distance is decreasing. So they are getting aged. So this is exactly the idea that even if I don't do anything, if I just stay where I am, I'll get aged, and the minimum sequence number will also go up. Ultimately, G will become equal to minimum sequence. That is when it is a target for eviction. So any page replacement algorithm would like to leverage temporal and spatial locality that we know. Make proactive decisions such that whenever you want, space is available. And heuristic should be simple, but the overall setting should be complex. Should be easy to explain, understand, and verify. So as usual, what we have appreciated throughout this course, maintaining the right kind of data and data structures is crucial, is very, very important. So the first is a struct LRU vec, which actually corresponds to a zone. So for every zone, we have an LRU vec. If you would recall and you would go back to the zone data structure, you would see that that had a pointer to an LRU vec, which maintains all the LRU information. All right. Then for the entire zone, two counts are made, two counts are kept. For anonymous file pages and file, you keep a count of the number of refaults. A refault is a situation where a page was evicted from memory and then it was quickly accessed. So that is clearly a mistake. A refault is clearly a mistake because you thought that this will not be used, hence you evicted it and then very soon it got accessed. So the number of refaults are maintained separately for anon pages, cumulative, and file pages, cumulative. So this is an important piece of information as we shall see, because a lot of statistics are kept separately for anon and file. Then we have an LRU generation struct which maintains information about the generations. And we have something called state, which maintains the state of proactive page walking. Because as I said, when you're not doing anything, you do a little bit of walking of page tables and you try to see if there is any old page not accessed, you try to push it down into swap space, clean up the space in memory. So this is basically proactive walking of the page tables or proactive flushing of pages. And the former one, LRU gen, this maintains information about the generation. So maximum sequence is the largest sequence number and the minimum sequence is maintained separately for anon pages and for file pages, right? For anon and file, you maintain them separately. Also, the thing is that you don't want to be very reactive in the sense that you do not want to increase generation numbers very quickly, right? Or let's say that you don't want to evict something very quickly. It was just brought in, it's getting evicted. That is why every time you create a new generation, you maintain a timestamp of when it was created. So that generation numbers are not increased too frequently. And also evictions don't happen very frequently. The algorithm has breaks. All right. Otherwise, it will become a bit too reactive. Then what you do is you maintain a linked list of pages, right? Pages or folios, it doesn't matter because in Linux, a folio is quickly replacing a page. And how many linked lists you maintain? So for every generation, for every type, anon or file, and for every zone. So essentially for every zone and then for every type, which is anon or file, and for every generation, you maintain a linked list of pages. So if you decide later that for the file type and for generation number 5, I want to evict all the pages, or maybe just go through the linked list and find the pages that are worthy of eviction. This will easily give you an entry point. You can just traverse the linked list, whatever you want to throw out to the swap space, you can. All right. So this much of minimum state is maintained, which is a generational state, timestamps, and a linked list of all the pages. And this is essentially a 3-dimensional array where every entry is a linked list, right? And what are the access, the zone, the type, and the generation. Coming to LRU gen state, the idea here is that I want to proactively walk through a zone, find things that can be cleaned up. This is called zone shrinking, and send them to the swap space. So this is the current sequence number that I'm walking. And what I do is all the struct. So remember the struct from task struct. This is the structure that maintains the maple tree and page table and everything. So I have a linked list of structs. I walk this linked list of struct. So basically, I have a head and a tail pointer. So let's say the tail means that I have fully processed this struct, which means I've gone through its page table and whatever pages need to be sent down, I have marked them. And head is the point which needs to be processed, right? Currently, I'm processing the head. Then we will look at, then there is an array of Bloom filters. We will see what they are used for. We don't know what they'll be used for, but we know what a Bloom filter is. A Bloom filter is a data structure that checks for set membership. Given an item, it will tell you whether it is present in a set or not. Bloom filter can give you false positive errors. It will never give you a false negative. That is the property of the Bloom filter that we will use. All right. And the page walker is basically an entity whose job is to walk and clean. And the walker state is the walker state. And you could have one walker, you could have multiple walkers, or multiple walkers are separate threads that are walking. So the first thing that you would like to do, so if you would recall when we had discussed the WS clock and WS clock second chance algorithms, what is the first thing that we had discussed? We had discussed tracking accesses. That was the first thing. And there we had said that, these dummy page faults have to be induced. So let us see how accesses are tracked in the kernel. It is quite similar, but there are some small differences. So previously it was used and unused. We'll not use that state. Instead, we'll use accessed and not accessed. So there is a function page table entry make old. So there is a make new also, it does the reverse. So there is a clear, so this what it does is it goes to the page table entry, and if it is accessed, which means it is new. So it takes the accessed flag and clears it, which means it's not new anymore. So in general, you would like to convert new pages to old. Old to new conversion, well, in some architectures may be required, but we will see there is a better way, right? We'll discuss that. But this is the broad idea that when you are clearing this flag, this is like saying that the page was accessed. In a sense, the page was new or recent, whatever you may want to call. Now it is unaccessed, which means it is old. All right. This is something that I would like my walker to do. That when my walker is walking through the page table, you keep finding new entries and keep making them old. So the key idea is to clear this field. So if it is old, which means it is not accessed, the next time the page is accessed, what do? What happens? Correct? So how the page is accessed depends upon the hardware. Because in this case, you are clearing it here, but you are not really going and clearing it in the TLB. But let's say if it misses in the TLB, comes back, then you will realize there could be a bunch of ways. So we will look at them. But the key idea is that broadly speaking, if something is old, it needs to be converted to new, and there is an access, you have some way of knowing about it. One way is that a dummy page fault is raised, which is the solution that we have seen with the WS clock family of algorithms. In this case, if a dummy page fault is raised, then it comes to this entry, you convert old to new, and you record that fact. The other situation, which is more prevalent on x86 machines, is that hardware sets the bit directly in the page table entry, right? And the next time an access is made, which means if it sees that it has a certain property in the TLB, then the hardware will have a circuit which will automatically go and convert not access to access. So in that case, there is no interrupt. And on x86 machines, the hardware does it directly. But there are architectures such as RISC-V that would require a dummy page fault. Howsoever it is happening, let's say that there is a way of converting unaccessed, not accessed to accessed, some way. So the key point is that if I have done this, the moment I scan, so let us say that I scan memory once, I find it is accessed and I convert it to not accessed. The second time I scan memory, if it is still not accessed, it means that for a long duration it was not accessed, otherwise the bit would have been set. So this becomes a target for eviction. That was broadly the idea in those algorithms also. It is a broad idea here also, but here it is somewhat more nuanced because you have generations, right? So in this case, you will not increment its generation. Ultimately, its generation will become so low that you would evict everything from that generation. Fair enough? So this is slightly more nuanced, but you get the broad idea that it is all about the accessed bit in the TLB and page table. x86 can set it directly, but other architectures raise dummy page faults. It doesn't matter how it's happening, but this is used to find out recency of access, right? That is the most important point. Now what happens is, let's look at, given that this is the basic mechanism, let's look at the different ways of proactively doing it. So kswapd is a kernel daemon that runs periodically. Its job is to age the pages and reclaim them. Aging the pages basically means incrementing the generation such that the generation gap between the pages generation and maximum sequence increases. Correct? Ultimately, it will become the lowest generation. It will get thrown out. Sometimes this can be done kind of on demand, where you want to allocate pages, sufficient space is not there. You would like to shrink. How will you shrink? By throwing pages down to swap space. In some cases, you can go for reclamation. Reclamation basically means that if let's say there is a file buffer, so a file buffer is a buffer where I have reserved a set of pages for file access, right? For my files, the moment I'm memory mapping them, I will use some pages to map their context to memory. Let's say there I've reserved 100 pages. Maybe I can reduce that 100 to 80 and move 20 pages to the general pool. Then over time, they can get aged and thrown out. But instead of they being used for specific use, I can convert them to generic use. Then at least any process that wants can use it. This is reclamation. So all of this is done here. So finally, when I want to evict, I call the function evict folios and they are gone. After reclamation, so either I do evict folios, which means throw them out from memory, or I reclaim their space, which means from specific use, I convert it to general use. Now the question is, when should I run the aging algorithm, right? The aging algorithm essentially increments the maximum sequence number, and once it has thrown out everything and initiates the process of throwing out everything from the minimum sequence number, such that the minimum can be incremented and the maximum can be incremented. Think of it as a sliding window. It is shifted like that. Increment the maximum immediately, and after cleaning up the lowest generation, increment the minimum. So what you would like to do is LRU gen max sec has the latest generation, and min sec has the latest for anon and has the earliest for anon and file respectively. What we would like to do is that the number of generations, which is max sec minus min sec plus 1. So this is the number that we have. This we would like to be greater than equal to min NR gens, right? The minimum number of generations. In fact, we would actually like it to be equal to minimum of these many generations, but we'll look at that later. So if let's say there are too few generations, you will want to increment the maximum sequence. If there are too few. And given that both of them increase, as I said, if the minimum increases and the maximum increases, but the generation remains where it is, ultimately it will catch up with the minimum and is going to go. So this is why a sliding window is maintained. So if I look at the process of aging, the process of aging uses some simple formula. All right. So the number of generations you would like to maintain are actually, so I stand slightly corrected with respect to what I said on the previous slide. The number of generations I would like to maintain is actually min NR gens plus 1, right? That is roughly what I would like to maintain as the number of generations as kind of my ideal, as my target. So which means that how many maximum generation pages should be there? Let's say if this number is lambda, lambda should be equal to total divided by this number over here, which is min NR gens plus 1. Is that correct? So what I do is that I define two thresholds which are kind of around this number. All right. So lambda is total. So let's say lambda is total divided by this number. So total divided by min NR gens is something that is slightly larger than the ideal value, correct? Because if I reduce the denominator, any fraction is going to increase. So if I reduce this from min NR gens plus 1 to min NR gens, then total by min NR gens is more than the ideal value. That is all right. So that for me is like an upper limit of comfort. If the maximum generation pages is greater than this number, which means greater than total divided by min NR gens, which you can clearly see is greater than lambda. All right. Then I will conclude I have too many pages at the maximum generation. I should increase the number of generations. Similarly, if I have too few pages which are in the earliest generation, which means if min gen pages is less than total divided by, this is again, one more safety margin. If this is actually too little, right? Because if I'm increasing any denominator, any fraction will reduce. So this number is actually less than lambda. All right. So what is happening here is, this means there are too few ultra old pages. This means the rest of the pages, there are too many and they are kind of packed between too few generations. So I should spread them out. That is why it's a good idea for me to actually increase the number of generations and try to get rid of these min gen pages as soon as possible, because anyway there are not many of them. So I should speed up their eviction. So the question is, when do you decide to age? You decide to age when you have too many ultra young pages, or when you have too few ultra old pages. Because you have too few ultra old, which means the rest that are non ultra old are kind of packed into limited number of generations, correct? So this is the aging process. The moment I age something and I tinker with these sequence numbers, this sliding window of max sec and min sec, I walk through all the structs, I walk through the individual page tables, and then so if you would recall, in page table I have a PMD, right, just above the PT. There I see, is it predominantly unaccessed or not, which means that if the entire PMD is old, then what do? I will try to skip this. All right. So the main idea here is that I do a page walk. In the page walk, I try to only access those PTs which are young. So as the young ones, I'll convert to old. Right? I'll record the fact that I'll increment some counters, I'll convert them to old. So then why am I doing that? I am doing that to again refresh my state, right? Because if something is young, I will promote it to the newest generation because it has been recently accessed, and then I will basically move on. But then because I'm promoting it, I'll convert access to not accessed. Now what I want to do is I want to skip all of those PMDs, which are the second lowest level tables. If let's say most of it is old, I would like to just skip it. I'm not interested. This will speed up my page walk process. How do I do that? I do that by adding PMD entries to a Bloom filter. So if a PMD is predominantly young, I add it to a Bloom filter, right? Now, given a new PMD, I check for membership in the Bloom filter. A Bloom filter will never provide a false negative. So if it says that yes, this is young, it may be right, it may be wrong. But if it says this PMD is mostly old, then you can say that, which means it is not young. Because false negatives never happen, it is 100% correct. So the entire PMD can be skipped. All right. So what is the big picture over here? The big picture over here is that I first see whether I should run aging or not. Aging means what? Incrementing the maximum sequence number and ultimately incrementing the minimum sequence number, which means shifting the sliding window. What effect does that have? Well, the effect that has is that if I have not been accessed, ultimately my generation goes down, down, down and down relatively, and then I get thrown out. After I've increased the sequence numbers, I should walk the page tables and see this accessed, not accessed business, right? So I do an accelerated walking. If there are large regions that are not accessed, I don't have to do anything. Because they are anyway at the lowest generation, they will get thrown out. If, however, they are accessed, I convert their access to not accessed and I promote their page or folio number to the latest generation. Does that make sense? So this is kind of similar to the WS scheme of algorithms, where I just did one scan and then a second scan. It is quite similar to that. In this case, instead of using a 1 bit, I am using a set of generations, that is all. And every time I age, I basically move the sliding window like that. Right? This is like this, then I move it like that, like that, like that. So if I'm static, ultimately the bottom of the sliding window will come and hit me. I will become the earliest, and it is time for me to be thrown out. So the eviction algorithm is actually quite simple if you think about it. It is basically that we have these lists. These lists maintain that for a minimum sequence number, how many pages are there. If let us say that any list is empty, if any list is empty, you can increment the minimum sequence number. If let's say it is not empty, then you should consider it for eviction. Correct? So it just is that this eviction process is slightly more complicated, but it is not very complicated. So for every generation, I would like to create a sub-generation. The sub-generation is like a generation, generation point, something like 1.2, 1.3, 1.4, like that. So what is a sub-generation is that after I am promoted to a current generation, I record the number of page accesses. But this page accesses is being recorded using our special mechanism, which is that you convert it to unaccessed, and the next time you scan, if you find it to be accessed, then you actually increment by 1. It's not actually the actual number of accesses, but it's the number of these bit conversions that we see. So let us say that you saw 2. Then the number of page accesses plus 1 log to the base 2 is known as the tier. The tier is the subgeneration. For example, let us say you recorded 6 different such changes. Then its tier or tier will be log of 7 to the base 2. Alright, so far so good. And so in this case, let's say if there are no accesses, then its tier is 0. Right, because it's log of 0 plus 1 to the base 2. Sorry, it's to the base 2. And so this is going to be 0. Then if there is 1 access, it is going to be 1. If there are 2 accesses, it is going to be log of 3 to the base 2. So what should you take, the floor or ceiling? So 3 and 4, you take the ceiling. So basically in this case, what you do is that you take the ceiling of this, and that is very easy to do using bitwise operations. So then what happens? Every page or folio has a generation, and you are also recording how many times you have seen it to be accessed using our mechanism. A log of that number plus 1 is its tier. And what I want to do is that I want to, so these things I'm tracking. Number of accesses easy to track. If I'm scanning the page table, last time I saw it to be not accessed, this time accessed, okay, I record 1 access. Correct. So even for files, I can do the same using the file access system calls. So the first tier, right, will basically be the number of single use pages, because these are the ones that have not been accessed. So what will the first tier, like tier 0, contain? Tier 0 is log of 0 plus 1 to the base 2. Log of 1 to the base 2 is 0, which means that these have never been accessed. They were brought in, they have remained clean ever since. So they clearly should be your first targets of eviction. So what we will do is that we will compare the minimum sequence values of file and anon, do a little bit more of comparison, but the basic idea is to get rid of the oldest generation. But we will see that using the notion of tiers, it is slightly more nuanced than this, as is the case with the kernel. So we will see in a second how the tier information is used. So here what you want to do is that, let us say, the first choice you need to make is, should I evict a file page or should I evict an anon page, right? Which one is the one that I should evict, file or anon? So they will have different sequence numbers, but I need to find out which one should go in their minimum sequence numbers. So I will compare their tier 0 pages. Okay. In their tier 0 pages, these are the clean pages. So what will I do again? The question I need to answer is, I have anon pages and file pages. Which type of pages I should evict? So what I will do is, within its minimum sequence, I'll take the minimum sequence of anon and I will take the minimum sequence of file. I will compare their tier 0 statistics, and tier 0 is the clean unmapped, clean pages, which came but nothing happened. So what I will compare is basically the refault rate. The refault rate is basically the number of refaults divided by the number of pages in that category, right? That is a refault rate. So if you have 100 pages and there are 20 refaults, your refault rate is 20 divided by 100. So let me call this a normalized refault rate. So the normalized refault rate, I will take this number and I will divide it by what is called the gain. The gain is an interesting concept. The gain represents my desire to evict a certain kind of page. Let us say that I have configured the kernel in such a way that I want to evict anon pages. I want to give preference to file pages. That is just my desire. As a kernel builder, that is simply my desire. So what I will do is I will set the gain of, let's say, anon to very high, and I will set the gain of file to low if I want to evict anon. If I want to evict file, I'll set the gain of file to very high, right? So for given a certain kind of pages, I will compute this quantity normalized refault rate divided by gain. The first is the refault rate that is being observed. Gain is my desire to throw out pages of this type. All right. I will compare this for anon and I'll compare this for file. The same quantity. Normalized refault rate divided by the gain, but of course these gains are different. One is gain anon, one is gain file. If I compare the same, so ideally you would like both to be equal, correct? In the sense that if my desire to throw out is high, the default rate should be high, should be proportional to it, so the ratio should be the same. Assume that the ratio is not the same. If the ratio is not the same, and let us say for anon it is lower, which means that the number of refaults is not commensurate with my desire to evict anon. So I should increase the number of refaults for anon. How can I increase the number of refaults for anon? By evicting anon more. Correct, because refaults cannot be reduced, they can be increased, right? Let's go with that. So I will evict anon more. Well, they can be reduced if I evict less, but in this case, I'll just evict anon more because the decision has to be made for the current eviction. So what is the quantity I'm trying to equalize? The quantity I'm trying to equalize is the observed refault rate divided by my desire to throw out a certain kind of page. If my desire is high, the observation should be high. Let me assume that the observation should be proportional to my desire, which means the ratio is a constant. This basically means NRR by gain of anon should be equal to NRR by gain of file. If one is less than the other, I'll choose the one that is lower for eviction such that the default rate increases and the ratios move towards equality. That is exactly what I'm doing. Some control theory terminology has been borrowed in the sense the set point is anon, the process variable is called file. So don't go into why it is named that way. But the logic is that if there are too few refaults in the system, let's say less than 64, then I would choose files for eviction. Because files, they are already, a copy is there in a file, right? Why not? Otherwise, I will compare the ratio of NRR by gain. And if it is lower for PV, which is for file, then I'll evict file. If it is lower for anon, I will evict anon. As simple as that. So this parameter or the gain is quantified by this parameter called swappiness. So the gain is swappiness for anon and 200 minus swappiness for file, which quantifies your desire. So the first thing that you do is you identify all the folios that are to be evicted, and then the next thing is you evict them, right? So the algorithm in this case is simple, that you identify everything that is in need for eviction and then you evict them. So you do a little bit of additional bookkeeping. So if I were to show you the algorithm is quite simple. That so this is the place where I'm trying to choose. So let us say the swappiness is 0. So this is a special value because the swappiness should be between 1 and 200. I choose files. If let's say anon has a lower sequence number, I will choose anon. Otherwise, I will look at the limiting values. So of course, see, there is not a lot of logic for this piece of code. Some of it is also empirically inspired, experimentally inspired. If the swappiness is 1, I will choose file, which is 1 extrema. If it is 200, I will choose anon. Otherwise, I will do a competition between them and compare their normalized refault rate divided by the gain. All right, so this is Linux's logic that if anon sequence number is lower, you pick anon. But if file sequence number is lower or equal, then you do a competition if swappiness does not have a special value. The competition is like this. So first is anon swappiness is gain is swappiness. For file it is 200 minus swappiness. So what you do is that in this variable, you compute normalized refault rate by gain. In this variable, you do it for files, and then you just compare them. So this comparison we have seen, it is just comparing the ratio. Whichever one is lower, you choose that for eviction. So what you do over here is that whenever you are trying to find out, should I evict a file page or an anon page, you compare the statistics for their tier 0. Tier 0 are those clean pages. Those clean pages we would like to be unmapped. But the question is, which one? So let us say I choose this type, which could be any type, file type or anon type. The ratio of NRR by gain for this is lower than the corresponding ratio of the other type, which is why this was chosen in the first place. Then what I do is I take its tier 1, which has seen some accesses, and again try to compare it with tier 0 of this one. If it is still lower, I keep moving to tier 2. If it's still lower, I keep moving to tier 3. So assume that till this point, tier 2 was lower than this, but tier 3 is more and tier 4 is more. But anyway, I don't check for tier 4. So these are some higher tiers that are showing more accesses in the type that needs to be evicted and more accesses as compared to clean pages of the other type. So let me do one thing. Let me give these pages an additional chance. The reason I'll give them an additional chance is because number one, they are being accessed, right? That is the first thing. Second, their refault rate is not very low. It is at least more than tier 0 of the other type. So let me give them one more chance. If they are not able to then, let's say, perform, in a sense, still if they reach a very low generation, then I will see. But for the time being, they appear to be good citizens. So let me give them one more chance by maximizing the sequence number of the pages in tier 3 and tier 4 in this example, right? Such that they get a second chance, and then we will see. If they still keep falling down, we'll again use the same test, but broadly speaking, so the key takeaway point is that making a decision between evicting a file page or an anon page is a difficult and challenging decision, right? It requires a lot of thinking. You are fundamentally comparing the normalized default rate with divided by the gain. So where is the gain coming from? The gain is like a fudge factor, which is your desire to evict pages of a certain type, and you want your observation to be proportional to the desire such that the ratio is a constant, and to maintain the ratio, you are trying to increase the default rate for types where it is low. That is the broad idea. So given that we have seen the logic for selecting either the anon type or the file type over here, where the basic idea is simple. We compare the statistics for tier 0, which is the normalized default rate, divided by the gain. And clearly for the one that is lower, we would try to increase the default rate by an eviction. That is why we do that. And for some of the tiers whose access frequency is higher, they are given a second chance. And of course, in this case, the default rate is also higher. So that is why they are given a second chance, because they tend to be now. So if you are accessed a lot and your refault rate is high, that means what? Your accessed a lot means the page is popular. The refault rate is high means consistently a mistake is being made and this page is being evicted even though it should not be evicted. So it makes sense to take both these factors into account and promote these pages which are there in these tiers to the largest sequence number. It makes sense. So the rest of the isolate folios function, so what you basically do is that you pretty much scan all the folios and you go through all the folios and see all the ones which are evictable or not. So you do a full page table scan. So in the page table scan, we saw a lot of things happening. The first is that if something is evictable or worthy of eviction, then you mark it for eviction. The second thing is, if you see an accessed page, you convert it to unaccessed, right? And you record the fact that it was accessed, right? So let us say mark for eviction. Then let's say you check the accessed bit. It has been accessed, then you make it unaccessed, but then you promote its generation. So whenever you say it has not been accessed, it means its generation is also promoted. Then you update the Bloom filter. You update the Bloom filter such that subsequent page walks are fast. So you do all of these things where the main aim is to do some amount of bookkeeping. So the main idea is like this: you do some immediate work and you do some deferred work or do some bookkeeping work. That will be useful later. So the immediate work is that you are finding pages for eviction, that you will. But given the fact that you are scanning the page table, you can do a little bit more. Little bit more would be checking these access bits and updating your Bloom filter such that, number one, your state remains up to date and subsequent page walks become fast. So what we have is, we have evict folios, so where you isolate them and you find what is the type to scan, what should be evicted and what not, and then you scan them. And after you have scanned and you sort of have a list of what is it that needs to be thrown out, then the information flows backwards. And note that any process of scanning is also a process of maintaining, updating and bookkeeping as well. So then, for every zone, you pretty much know what is it that needs to be evicted or thrown out, or how the zone needs to be shrunk. So then, what we do is that all the folios that are pointed to by the minimum sequence, the type chosen for eviction and the zone, we have already scanned and found the folios that need to be evicted. But prior to actual eviction, we do a few more checks. Just marking for eviction is not good enough. The process of marking has to be subject to a few more checks. So when do you mark? You mark when you feel that it has not been used for a long time. So its sequence number is the minimum. And the fact is that as compared to the other type, its expected refault rate is somewhat low. So it should be brought up, right? Such that it equalizes to the other type. So then you will try for eviction, but what if the folio is pinned? So there could be folios which are sets of 2 to the power k pages where you have pinned it. You don't want it to be thrown out of memory. So then you clearly cannot evict it. It's like an override signal. If it is already being written back, you would want that to happen instead of putting another parallel eviction on top of it. If, let's say, after scanning it got recently accessed, then it makes no sense to actually evict it. There could be different kinds of race conditions where different threads are trying to acquire it. It's much better to kind of calm down, wait for all of those concurrent events to finish, and then basically finish the eviction. So once this has been done, we return the number of folios that can possibly be evicted, which is after this filtration process, and the variable scanned will have some of this information. and the list variable will have a list of all the folios that you need to evict. So, given the fact that we have a list of folios for eviction, we then need to do some more bookkeeping and start the process of actual eviction. So, at this point of time, what we have done is we have figured out what all needs to be thrown out. So, first is that we find is something being actually evicted or being reclaimed. Eviction and reclamation are two separate issues altogether. Eviction means from the memory to the swap space. Reclamation means it was being used for a specific purpose, for example, to store the buffers associated with a file. But let's say that, why do you need these buffers? Because when you are reading a file into memory, it has to be kept somewhere. So you reserve a set of pages for it. But let's say you're reserving too many pages, what is the requirement? It is kind of tied up in one purpose. At least let the page move to the general pool. You do that. That is reclamation. And so after a folio that, so then also, if other concurrent events are going on, you sort of stall this process. After it ends, once you try to evict a folio, you also try to slightly look around in the neighborhood of the folio that is being evicted in its page table. So let us say that this is its page table. I can represent it as a tree. This folio, it's a leaf, right? So it's a page. A page would be a leaf, but a folio would be slightly at a higher level. So let's say this wants to be evicted. If this wants to be evicted, you want this to be evicted, you slightly look around in the neighborhood of this. And then there, if let's say you make a few pages old, in the sense you clear the access bit, so you do a little bit of bookkeeping right there itself. Also, you note down any PMD entries which are predominantly young, which means that if you get a PMD and most of the pages in the PMD are young, then what you do is that you enter this address in a Bloom filter saying that this is a young PMD, such that when we are traversing, we can actually skip some of the predominantly old PMDs, right? From the false negative logic that a Bloom filter never gives a false negative. So let us say if your Bloom filter stores a list of young PMDs, and let us say you don't find a PMD in this Bloom filter, it means that for sure it is old. If it is old, it does not have to be scanned. That is the logic. So you are updating the Bloom filter. You are kind of poking around, right, in the same virtual neighborhood. So what you are seeing is maintenance and updating is primarily finding out if there are accessed pages. Accessed is always converted to unaccessed and the generation is incremented. That is all that you do. And then for the PMD level, you enter primarily young PMDs into a Bloom filter. That is what you do. So at this point, large folios can also be broken down into smaller folios if there is a need. And then you do the step 5 is the final write back function. In this case, you free your buffers and you would flush the entries from the TLB and write them back. So when something is being written back, it has to be flushed from the TLB. The page table has to be updated to say that now it is in the swap space, and you tell your IO subsystem to actually write the page back, right? So writing back involves first identifying. So let's look at the broad steps. So you first identify what is to be written back, right? So first identify what is to be written back or evicted. Then you identify when should I do it? Should I wait for some critical operations to finish? Right? Most likely you should, because then there is a correctness issue. So when? After that, when you have decided you'll write back something, you sort of poke around in the neighborhood, mainly for finding pages that have been accessed and for updating the Bloom filter. So you just do a little bit of bookkeeping. After bookkeeping, once that is done, then you start the process of write back, which involves what? If let's say they were assigned to some kernel buffers or file buffers, you free the buffers, you flush the TLB, modify the page table, and you write back. That is all that you do. If I were to look at LRU gen look around, so what it does primarily is that it sort of looks around in the same VM area, in the same virtual memory area, in the same VM area struct, it sort of looks around. So you consider the memory space that is mapped by one entry in the PMD. So PMD would map a lot of PT entries, right? It would map 512 page table entries because it's a 9-bit. See, out of that, you limit the considered region to 64. So you take a window of 64 pages. So that is my look around size. You iterate through all the pages in this set of 64, right? So if you're, let's say, evicting some page, you go to its PMD entry. Out of those 512, you choose a window of 64. You iterate through them and you perform your bookkeeping. The reason this is done is because if something is being thrown out, let's look at what is happening in its neighborhood. So if it's an old page, nothing needs to be done. Else, if it is a young page, find the folio associated with it and mark all the pages in the folio as old, which means you will clear their access bits. And then what you will do is, if the generation of the folio is not the maximum sequence, you just record the page number. Just record the page number in a data structure. Then what you do is, you look at all the young pages in that PMD. If it is more than a threshold, it means it's a young PMD. So you add it to your Bloom filter, right, for efficient page traversal in the future. Then what you would do is that all the pages that you had recorded whose generation number was not equal to the maximum sequence number, you set their generation to the maximum sequence number. So what is the broad idea? The broad idea is that I want to evict this page. So this page is a page table entry which is pointed to by a PMD. So I go to its top level PMD. A PMD is mapping how many pages? 512. Out of that 512, I choose a set of 64. All right. Then what I do is I iterate through this set of 64. For each of them, I start doing some bookkeeping. Bookkeeping would be if it is accessed, make it unaccessed and set its sequence number to the largest sequence number or the latest generation. And then if that PMD itself appears to be young, because you're looking at this window of 64, let's say that predominantly that 64 is young in the sense recently accessed. Then I add that PMD to a Bloom filter which contains the list of all young PMDs. Why do you do that? The reason you do that is because later on, if I provide it a PMD address and I ask the question, is this PMD young or not, I may or may not get the correct answer. Because Bloom filters are known to yield false positives, but they will never yield a false negative. Which means if the Bloom filter says it is not there, you know for sure that this PMD is old, so it can be skipped. Because the bookkeeping is happening on what? It is happening on young pages. It's not happening on old pages. So our main idea with the MGLRU algorithm is that you find recently accessed pages and you keep incrementing the generation. And then automatically pages that are not being accessed will fall back and will ultimately become the earliest generation. And then they will be considered for eviction. That is our broad idea, that this is the point, the sliding window goes up, you become the minimum and you get thrown out. So the Bloom filter, the way it is used, I think we have discussed it several times, still a slide is due. So case swap D is that periodic kernel daemon that runs and tries to age pages. Sometimes write commands do it, and page allocation modules. All of them will try to age and evict pages. They will call the function walk means walk the memory map, and it will do the same, updating generation, converting access to unaccessed. Old entries are obviously skipped because we have nothing to do with entries that are old. All our processing is on entries that are young. While walking the page tables, Bloom filters help you improve performance. And needless to say, Bloom filters addition is easy, deletion is very hard, which is why Bloom filters have to be periodically reset. right? So that is a limitation of the Bloom filter structure. Of course, there are other structures called counting Bloom filters and so on. But again, they are not that simple and easy to use as, for example, this Bloom filter is. So let us now look at the concept of thrashing again in the practical precincts of the MGLRU algorithm. So what was thrashing? Thrashing was that I boot up a machine and I want to open, let's say, Edge. It's taking some time. I run out of patience. I start Chrome. It's taking some time. I run out of patience. I start Firefox. So you need to understand that the reason it is taking some time is because if this is, let's say, the memory size and this is the page fault rate, then till a certain point the page fault rate will be very high, then it will start to reduce significantly. This point is known as your working set. Say the working set is not fitting in memory, then what will happen is that thrashing may be observed because your working set is not fitting in memory. So most of the time you are fetching pages, but when you are fetching pages, you are evicting some other program's working set. So then what is happening is that the CPU is switching to the other program. It is not able to run, and all the time the CPU load is low, so you are scheduling more programs on the CPU. So system will crash. That is why, if you would recall, we had a timestamps field in the LRU data structures. That basically said when a generation was created. So the idea here is simple. That do not evict a page unless it is more than n milliseconds old in memory. Which means if it comes to memory, it's guaranteed to stay for a certain amount of time. This will ensure that this continuous tit for tat page flushing does not happen. So n is equal to 1000, which is 1000 milliseconds is 1 second is a good value, which means that let's say if a page has come in, let it remain for 1 second, which means that whichever program started, let its pages remain for 1 second before it is actually thrown out. This limits thrashing behavior to a large extent. Assume that in spite of that, the working set cannot be maintained and the page fault rates and the refault rates are still high. Then, based on a couple of thresholds, it has to be decided that thrashing has set in, which means the load is simply too high, the working sets are not fitting in memory and they are simply evicting each other's working sets and not doing any useful work. At that point of time, we have an out of memory or killer that comes into action and terminates a few applications such that things remain fine. This behavior, so the overall behavior of the MGLRU system is configurable. Okay, it is configurable. In the sense, we have a minimum number of generations, maximum number of generations, and the swappiness. They control the behavior. The number of generations basically says, it talks about your aggressiveness of eviction, right? That what is your fine-grained level of information that you maintain, how many second chances do you give? Because if you have a lot of generations, when you access something, it becomes a very high sequence number. Then it gradually falls, right? So it does not fall, it remains there, but a minimum keeps climbing up. So then this determines for how long a page will stay in memory. Similarly, swappiness gives the relative priority of file and anon. So these behaviors, along with some thresholds like this n is equal to 1000, they determine how your memory system will react to load. And clearly a good system should set it correctly based on the workload. So the main idea for any Linux engineer is to figure out the workload and on the basis of that set these parameters. So such that you do not observe thrashing, you do not observe a lot of slowdown and things still work. So this finishes this lecture. So in the next lecture, we will look at kernel memory allocation.